Sauce here. This is a video lesson on volume of revolution using shells. And we know the best chance we have of getting these problems correct is to slow down and use the given information to draw, visualize, and label before attempting to set up the integral to calculate the volume. I have a problem. Find the volume of the solid found by revolving the area under the function e to the x on the closed interval from 0 to 2 around the y-axis. I have the graph of the f function given, e to the x, it's exponential, base e, and I've highlighted the region under that function on the interval from 0 to 2. I have a symbol which looks like a circle in perspective to label the line that I'm going to rotate this region around. And immediately I notice that it's not the x-axis, it's the y-axis. So what does this solid look like if this region was to rotate around? I'm visualizing a bowl. I'm going to draw it after I have some more information. How does this region get used? If we have a function value, one chosen in the middle as a representative function value, and draw a line to represent the value of the function, how does that line rotate around the y-axis? This is not going to look like a disk. Disks are created in this situation with a vertical line, often revolving around the x-axis. It spins around making a disk or a filled-in circle. But the movement of this line around the y-axis is fundamentally different. That line is going to go around and stay vertical. The shape that gets created is like the sleeve of a soup can, the paper label on a soup can. It would help us to visualize what that might look like by focusing on the point on the function and thinking of it revolving around the y-axis in a third dimension. It would trace a path if it was able to come out of the paper much like this. If the bottom of the line were also rotating around the y-axis in the third dimension, it would trace a path that was circular. But in this case, it's not a washer that gets created because the path of all the points along the line in between these two would then also rotate around as if they were attaching these two endpoints that create these two circles. What gets created by the motion of that line around the y-axis is a cylinder. But the shading, the area that this line is going to represent, doesn't include the top and the bottom of that cylinder, the two circles. It's only the side of the cylinder. It's the shell, like a soup can label, that wraps the cylinder. We could think of that shell if we were to start with a cylinder and shade the inside of the cylinder as if the top and bottom were cut out. We want to be reminded that a cylinder has a radius. If we cut the label on a soup can and began to unfurl it or unfold it, we could have or show or attempt to depict an intermediate step of having cut it or sliced it with some scissors, and imagine now that we can lay it flat. What would that flattened out soup label look like? It would flatten out to be a rectangle. In this situation, every function value, if it's represented by a vertical line, rotated around the y-axis, creates a two-dimensional region which is rectangular in shape. In 3 dimensions, it comes from what we call a shell, that three-dimensional wrapped up soup label. But if we cut it and unfurl it, the geometry of finding its area is the same as finding the area of a rectangle with a base and a height. So how does the base and height relate to the function given? And how can I use the function in order to calculate the area of that rectangle? The height is the same thing as the value of the function that was the representative vertical line that got rotated. The height comes from the function values, in this case, e to the x. Where did the base come from? The base is a line that got unfurled. It was the top edge of the soup label that started as the circumference of the cylinder that got created. So when this point, or any point along the line, let's concentrate on the top one, rotates around the y-axis, it creates a circle. And that distance around got unfurled to become the base of the rectangle. So what is the value of the base? The value of the base is equal to the formula for the circumference of the circle, which is 2 times the radius times pi, or diameter times pi. So what is the radius of these circles? Well, the distance from the y-axis to this point, which is the radius of this representative slice that got created, is the same thing as the value of x. This point has coordinates x, e to the x. X is then the radius of the circles that are formed. And if x is the radius of the circle, then the base of the rectangle, the circumference of the circle that forms a shell, is equal to 2 times that radius x times pi. The area then of this shell, which is a rectangle that's curled up, is equal to base times height, or in terms of x, 2 pi x times the height, which is e to the x. I now have the formula for the area of the two-dimensional surfaces that I'm going to integrate or sum together to produce a volume. This volume is created by summing together an infinite number of infinitely thin shells. This is one representative shell. To get an idea of the solid that gets formed, I'm going to take the upper bound of my interval 2, and I'm going to form another shell, visualizing this point revolving around the y-axis. And this point. These are the 2 endpoints of the line, and so if the entire line was to revolve around the y-axis, then it would produce the outside area of the cylinder, or another shell. The lower bound of the interval is 0. a line or a function value at 0 is on the axis of rotation, so it isn't going to form a shell in itself. If I could visualize then the sum of all these shells to create the solid formed would be like a bowl, but the bowl would have a very square and stable base. In 3 dimensions, I might label this solid a bowl. How do I find the volume? I'm going to be integrating the formula for the area of the 2-dimensional shells, which is a rectangle. I'm going to be integrating 2 pi x e to the x with respect to x. And I'm going to do that for the first shell created, though it's a line, at 0. And I'm going to create an infinite number of infinitely thin shells at each value of x until I get to 2. The bounds of integration are 0 to 2. Now that I have the integral, I could take out the 2 pi, integrate x e to the x. Techniques for integration are not intended to be a part of this lesson, which is focusing on the strategy of using the shell method and setting up the integral. For this integral, we would need integration by parts. In the end, we would get 2 pi times the antiderivative e squared plus 1, evaluated at 2 and then minus evaluating the antiderivative at 0. We would get approximately 52.710. And I add the last 0 to show that this has been rounded to the nearest thousandth.